Hello, everyone. It's nice to meet you. My name is Wido Hanggoro. I'm going to talk about the general numerical weather prediction (NWP) of atmospheric model. It should be together with Mr. Erwin, but unfortunately, he cannot join in today's session. And maybe I hope he can join in the next asynchronous session in the discussion session. I'm working for the R&D department of Indonesia Agency for Meteorology, Climatology, and Geophysics of Indonesia, or BMKG. And in this online course, it's will be cover about the understanding of the general information about the weather prediction, the strength and the weakness of NWP. For the outline, we're gonna talk about the definition of NWP, and then the history of NWP, why we use NWP rather than the conventional one, and then we'll talk about the strength and the limitation of using this product of NWP, and I'm also will explain about type of NWP model, but it's not cover all the NWP model. I mean, it's only a sample of the type of NWP model. Okay, let's start. Let's talk about the definition of NWP. So literally, there's three words. It's numerical, weather, and prediction. So the numerical means literally it's about using the data or the number. It's also can be means of reference to the method. You know that the equation in the NWP, it's generally using partial differential equation. So it can be solved using ordinary or simple equation, a simple method. It should be solved using the numerical. The second word is weather. Weather in this NWPs mean the state of atmosphere. So it's related with the initial condition or the condition of the data, the first of the data. It's like wind, temperature, moisture, and pressure. So it's also referring to the time scale. And the last word is prediction. Prediction means the act of the declaration of future event. So it can be also for hintcast, forecast. So it generally a forecast for a past, present, or the future event. If you can see the picture here, so the NWP, it's simply modeling the atmosphere. So the process in atmosphere should be modeled in a model. So what is the numerical prediction? So there are many explanation about what is the definition of numerical weather prediction. First, I'm taking from the sciencedaily.com. So NWP is the science of predicting the weather using model. So the keyword is model of the atmosphere with the computational technique. So it's using the numerical technique. And the second definition is this model is based on the physical dynamical equation that govern the atmospheric flow. Also, the process in the atmospheric and written as a computer code. So it will be run in a computer code using the HPC or the supercomputer. And the data for the prediction it's using the initial condition or the initial state of the atmosphere. And we can say for the third definition is a set of mathematical equation of atmospheric processes and used to predict the weather based on current weather conditions. So the mathematical equation, it's same like the code, the atmospheric processes, it's the physical dynamical equation, and the current weather condition, and once again, it's initial condition. And the last one is definition from KNMI, the Meteorological Agency, Netherlands. So it's a bunch of equations that track and simulate change in the Earth. So it's the key is the same. So you have the model, you have the physical dynamical processes or atmospheric processes, and we use the current weather condition to predict the weather in the future state. In general, NWP consists of three components. First is the observation itself, the initial condition, and then the model. So the process of the dynamic and numerical process in atmosphere, it should be written in a code using the model, and then it run in the computer. So in general, success in NWP should be first, the code or the physical dynamical process in atmosphere should be realistic. It should be represent the real atmosphere, but it's hard enough because model usually only simple picture of the real atmosphere. And the second is the initial condition should be known accurately. So in NWP, initial condition is the main problem. If you can create the perfect initial condition, the result of the NWP, it will be better than you have the worst initial condition, because the initial condition in NWP is very crucial. And the last one is the computing technology. Without the high amount of computing technology, you cannot do anything because it was computing demand rather than statistic forecast. NWP is very use high computing technology. So this is the three key if you want to success in prediction using NWP. And how it's different from the conventional method. So before NWP was used in the world, the conventional method, like me, I'm also using the conventional method. So first, we have the observation from the station, from the radar, from the satellite, etc. And if the conventional method, we use the weather map, we draw it, the weather map, to know the flow of the condition of the atmosphere. And with the experience knowledge of the forecaster, you can define the future state of the atmosphere or the forecast. But the problem is it's very subjective, because the senior forecaster and the junior forecaster will be made or will be drew or summary, give the summary of the future state is very different. So it's very subjective. But if we are using the NWP, in the observation, we can create the initial state or the initial condition, and then with the code or the model to calculate the future state of the atmosphere using the numerical integration. And then we use the interpretation using like displaying software like GRADS, NCL, and so on. So the result will be objective. So this is the main difference between this conventional method and NWP method. But you should take note that in NWP, you need the telecommunication, you need the objective analysis like data simulation, and also you have to know about the numerical model itself. You have to know the technology, like most of the model run in Linux operating system. And then after that, you also have to know about how to display it using the graphical application like GRADS. The symbol is a GRADS. So this component should be mastering first if you want to use the NWP prediction. So now we start to the history of NWP. So if we're talking about the 100 years of progress in forecasting and NWP application, we can divide it into 4 eras. The first era is from 1919 to 1939. The prediction only used the maps from the observation and using the simple statistical method like extrapolation. We can draw the maps of the weather map. And the second era is from the 1939 to 1956. So we already have the more increasing science understanding. So the application especially used for the aviation. And in this era also birth of the computer like ENIAC. We will talk about it later, because the computer is the key of the rise of NWP. Without the computer, we cannot do anything with NWP because it's very complicated if we calculate it manually. And the third era, or the advent of NWP, and unfortunately is down of the remote sensing, because we can use the NWP for the prediction of the atmosphere. So in this third era is the rise of NWP. And the last era is 1985 up to 2018. So the NWP is already mature, and we use a lot the NWP product like to aviation, to transportation, to anything in human activity. So it's already mature in this era. So if we're talking about the early development of NWP, so first the Cleveland Ape in 1890. He wrote a book about the physical basis of long-range weather forecasting. So he said that meteorology is the component of application of hydrodynamic and thermodynamic the atmosphere. So it's very basic that Cleveland Abe already stated that the physics and dynamic is the equation that govern the atmosphere. And he also proposed the mathematical approach to forecast. And the the Wilhelm Bjerknes. Sorry if I'm not the wrong mention, I'll spell it. So he also set down a two-step of plan of rational forecasting. First, he set the diagnostic step, which he thought that the importance of initial state of the atmosphere is from observation. So it's already known that the initial condition is very important, and it determined using the observation. And the second one is the prognostic step. So it's the law motion of the calculate. So it's the atmospheric processes. In Bjerknes era, he cannot solve the NWP numerically. See, he only developed a qualitative and graphical method, but at least he's already know the importance of the initial condition and the atmospheric processes. He already tried to calculate it, and the Louis Fry Richardson, so he's also continue the work of Wilhelm Bjerknes. So you know that the principle of govern the behavior of an atmosphere is a system of also mathematical equation, and he already apply using the finite difference. But because the computational complexity, the result of his calculation is a bad result. But he already in a right track. But the problem is at that time he cannot have the tools to compute the equation. But at least his work is the foundation of the modern forecasting, or NWP. And Richardson was the then known as the father of the numerical weather prediction. Okay, and reflect from the Richardson work. So at least there are 4 of a number of key development in the in NWP. First, there were profound development in the theory of meteorology. So it provided the crucial understanding of atmospheric processes, and then at least they're advanced in numerical analysis using the partial differential equation. So it can design the algorithm of the model itself. And the third things is the invention of the radio zone, because at that time the observation it's very limited. So with the radio zone and the introduction to a global network, so it can be used as the initial condition of the NWP. And the last one is, of course, the development of the computing system. So it can compute a very, very big task or problem in weather forecasting. So at least there are 4 component or parameter. So the success story is start in von Neumann era. He is the computer science that interesting in fluid flow. So his project is first is about the fluid dynamic flow. His mastermind or the man behind the design of ENIAC or the electronic numerical integrator and computer. Here's the picture of ENIAC. It's very big, and I think it's very complicated. And then in 1948, the American meteorologist is Jules Charney, together with the Rockner and Fjordhoff. He's using the ENIAC for calculating the NWP, and his prediction the geopotential height of the 500 hectopascal. And this guy or this team is the one who first success in predicting the weather using the NWP method. So it's also because the help of the ENIAC for the calculation. So what is so if we talk about the NWP today, you know that NWP is already used as general tool in many country, in the developing country, even a country who has not using I mean they're not running their own model but using from other center. But at least today NWP is very important weather prediction tool. So everyone is using weather prediction tool using the NWP rather than statistical. And many countries have their own system, while the rest, like I already said that before, the NWP output is used by the other country who cannot afford their own system. And today, the NWP already introduced the numerous effective improvement for a global and regional model. And in this era also, the ensemble forecasting is being present, like a GFS ensemble, SCMWF using the EFS, and the data simulation method to improve the initial condition. And then also the coupled model using atmosphere, ocean, land, because NWP cannot only stand only for himself. It should be coupled with the other model. And also in this in today NWP is also they use the same global model for weather and climate prediction, or people used to say it's seamless prediction. So generally it's very massive use of NWP. So based on the Korean Meteorological Agency, the NWP, the use of NWP at least divided into 4 case or 4 scenario. First is the first case is use the other center product, like like we only use the product if we're taking from the website, like graphic. So we only use the other center graphic and make the forecast. And the next step is we use the other center grid point value. So first we download the raw data and we manage to make our domain, and then we calculate or we modify the raw data, and we use the product using the software, and we make the forecast. So the difference is, if in the case one, we only take the graphic, so we cannot do anything with the graphic. I mean, it's only graphic. But in the second case, we have the raw data, so we can do like statistical analysis first, and then we draw it with the graphs or many graphic software, and we make some forecast. In the third case, this is the we I mean, many countries have it's general in many countries. So we run our own model, like WRF, CCAM, or many other model. So we run it ourselves, but we still use the initial condition from the other center, like GFS, like EFS, and many more. So we can modify the parameter here. Like, we want to use the other cumulus parameterization, we can change the microphysics and so on. And then we use the application model to modify the raw output, and then we draw it as a picture, and we make some forecast. So it's very general here in third case. And the last case is only used by the like America, Japan, Korea. They use their own global model. So they collect, they make their own initial state, and they use their own model to calculate the numerical integration. And using the application model, if they want to use the limited area model or the global model, and then they draw also the product. And usually the product in this step is used by the first case, and they make forecast. So it's generally the scenario of how the NWP is being used in many countries. So this table is showing us about the list of the forecast center. This is the deterministic global model in NWP center. So we have here SCMWF with the spectral, and then the UK for the UM model, and DWB for the icon, NCEP, and so on. So it's the main international NWP center in the world. And the progress here for the global, they have at least 9 kilometer in resolution. Yeah. Okay. So how does the NWP skill improve in today's era? First, the increase of power of supercomputer. So it's allowing to calculate the finer numerical resolution, like 1 kilometer, even 500 meter. And then the improve of representation of small scale physical processes in the model itself. And then the use of more accurate method of data simulation, because the problem in NWP is, once again, is the initial condition. With the perfect condition, it should have a better weather prediction. And then the increase of availability of data, because in many countries we already have a lot of station and also radar. and also the important thing is satellite because it's cover a big area of a domain. And then it's also because the increase of availability data in southern hemisphere, because it's very important because it's mainly in southern hemisphere is ocean. So usually it's very rare of the observation data. Yeah, in its graph we can see that the improvement of the forecast from year to year, from 1955 to 2000, and reflect from S1 score. Lower means better. So in 36-hour forecast, we can see that it's improving from year to year for the short range, but for the middle range, yes, it's also improving, but it's not as better as the short range forecast. And also for the NCEP operational for S1 score for the different model. So this is the EFN. It's lower, also better. So it's mainly improving. It's like it's already told before, because these four things. And this is the graph. It's the same, that the forecast skill is improving from year to year. So if you see that the better forecast is in the 3 days forecast in the north hemisphere. This is the bold line, and this is the southern hemisphere. Yeah, it's improving, and now it's almost the same for the north and south, because one of the reason is the observation. So now in the southern hemisphere is already have very it's not scarce observation anymore. Yeah, but for the 10 days, the skill is still very limited. Yeah, because we have the error. We will talk about the weakness of the NWP in next session. Okay, so now we talk about the strength and limitation of NWP. So yeah, NWP is very helpful, but at least like many other tools, NWP also have the limitation or the strength. So if we want to use the NWP, we have to know the limitation of NWP. So okay, so first, the strength is, so it's provide the future information of atmospheric condition. So it simulate the process, the physics and dynamic process of the atmosphere. So it's not like a statistical process that doesn't care with the physics or the dynamic process in the atmosphere. And then the second thing is NWP is reflect our best understanding of the motion and the process in the atmosphere. And then if we are using the NWP, it can project the wide area, like global, like synoptic, and we have a lot of parameter predict, like in one data we can have like precipitation, temperature, wind, relative humidity, and in one package. So yeah, it give many weather variable and wide area of prediction, and it also can be coupled with another model, so it can be improved of the prediction itself, and it's easy to access because we can have the graphic product that can be shared using a website, and also we can use also the OpenDAP or Great Data Server, the data access protocol for the environmental data. So it's very easy to access now using the internet. So this is the picture of the, if we are using the NWP, we can have the domain like this. It's a global domain, so it's very big domain. So we can know the synoptic scale or synoptic condition of in your area. So it's not only the point prediction, and we also can have the many product from international center like ACMWF, ICON from the German, GFS from US, this is from Canada, from the UKMO. So the main thing is, yeah, you can have a lot of a choice. So it also can be assembled easily. So now we're talking about the limitation of NWP. The problem is in NWP is the initial condition. First, because the lack of data, you know, if we're talking about the initial condition, it should be made from observation. And we also notice that not every part in the world have the data. Like in the ocean, it's very limited data. So the problem is the lack of data that can produce low accuracy of the initial condition. And the second thing is because the imperfect method of data simulation, because we use to fill the empty data using the interpolation, extrapolation, and it's make the data simulation once again, the initial condition once again is very limited in accuracy. And if we take a look at this graph, the initial condition, it's give major, I mean, it's give a big error than a total, I mean, than other error. So it's the root mean square of 500 HPA. And then we have also the model uncertainty here in deterministic. So if we only use a deterministic forecast, the result is not as good as if we use the ensemble prediction. But the problem is the ensemble prediction is also very expensive. And the second limitation is the computer code transformation of NWP basic equation is simplified from the real atmospheric processes, and sometimes it's very complex. So for the researcher or for the scientist, it's still poorly understood of the basic equation. And the next limitation is the resolution. So we have to know if we want to use NWP, which phenomena that we want to capture. So we cannot use the 50-kilometer resolution to capture the convective scale in example. So we have to know first which resolution it can be that can give explanation in which phenomena. So we have to be wise. So if we want to use the 50-kilometer, we can see the synoptic scale, but if we want to see the tornadoes, we cannot use the 50-kilometer. It should be under 3-kilometer grid resolution. But once again, to downscale the resolution, it's not cheap. You should have a big computation tools like HPC. And the other limitation is the orography. If we know that in NWP, the land is generally draw as a grid, so it's not reflect the best picture of the real orography. So it will give an error to the model itself. So yeah, some feature it's completely omitted. Like in this picture, the snow we can only draw three type of the land. First, the ocean, and the land and the snow. But in the real case, we have many different land use. Yeah, it's one of the problem. But in limited area model, the orography is better than a global model because it's the problem of the resolution, because the LAM usually use the higher resolution. The next limitation is the lateral boundary condition. Yeah, the problem is only exists in the LAM because in a global model, we don't have any lateral boundary condition in horizontal, I mean, but we have the lateral boundary condition in vertical. And the second thing is because the spin up problem, when we transport from the low resolution data to the higher one, and the problem is exists in the at the edge of the domain itself. So if we want to set the domain of the domain interest, you have to make sure that the part that we want to predict is in the center of the domain, because if you're interested in the edge of the domain, it will contain error. So like this picture is yeah, we can see the error in the edge of the domain. Okay, that is the lateral boundary condition problem. And the next problem or the next limitation is the large output. So this is the table give picture how many storage that you have to provide. Like if you're only using the WRF EMS, and sorry, it's in Indonesian word. So the spatial is 27 kilometer, and we predict lead time is 3 days. The input is 1.2 gigabyte and the output is 3.1 gigabyte. And with the existing HPC at that time, we can solve the equation in 8 hours, and we run it twice a day. So you can calculate how many storage that we need to keep all of this data. So it's also the problem in NWP. if you choose to run your own model. Okay, so the data itself, like I said before, you can access it easily using the DAP server. So there's many DAP server you can use or install. First is Grad Data Server here. It's very easy to install. And then a Grid DAP, and then Dapper, and the last one is the AirDAP, if I'm not mistaken. Yeah, you can use this DAP server to share your raw data in internet. This problem happened in Indonesia because you know that Indonesia is a very big country. So if we run the data in Jakarta and we want to disseminate the output, the raw data into to other city in Indonesia, we cannot send the whole data, like 3.1 gigabyte. We send it to other in Bali. It's very it's very hard to send it every day. And it's also people in Bali, it usually it doesn't care about the product or the forecast in Jakarta. So he want he all he only interesting in Bali domain. So using this protocol, you can cut your domain, your domain of interested, and only cut the variable that you need and draw it using the software. So it's very easy. So you're not sending the whole data everywhere. So you're only sending your data that you need. So now we talk about the type of NWP model. So generally, there is two type of NWP model. First, the global NWP model. So it's usually for the operational forecasting and run twice to 4 days times daily. Usually 0, 0 initial condition, 0, 6, 12, and 18 UTC. And it's usually short to medium range and global coverage that doesn't have the lateral boundary condition in horizontal, and it's usually hydrostatic. This model only care about the movement in horizontal direction, so it doesn't care about the vertical movement, and it's usually coarse resolution, generally in coarse resolution. But nowadays there's a many global NWP product that provide the higher resolution product. The second one is the limited area model or regional NWP model. So it's a local detail of the global model. So it's usually have a higher resolution than global model, but it still take a boundary condition from the global model. Like if we want to run in initial domain using the GFS initial condition, we are using the SCMWF initial condition. So yeah, it's higher resolution. So it can give the better representation of small scale event, and usually shorter forecast time. It's like 2 days, and it's cover only regional because yeah, the limitation of computation itself, and it's non-hydrostatic, so it care about the movement of vertical motion, and yeah, it's have the final resolution. So this is the list of the global model and regional model. So this is the general model that we use, the GFS, NOGAPs. This is Global Environmental Multi-Scale Model from Canada. EFS, we also use it for the forecasting. Icon, we're gonna talk about the icon in Cosmo model, and also ARPAGE from France. BMKG used to use this product in many years. And then for the regional model, we also use the WRF EMS, and also WRF for the ARW core, and also MM5 is the predecessor of the WRF. And also we have CCAM from Australia. So there's many global and regional model that you can choose. Okay, now we talk about the application of NWP or specific application. I'm not gonna cover all of the application in this section. I'm only give 3 example of the NWP application. Okay, first is the climate model. So the point is it's a similar process with the weather model, but it's considered not only physics, but also adding the biology and the chemical process in the climate model. And it usually represent the average of the region with the coarse resolution. And it's longer time step, because in climate we doesn't care about the specific time step. I mean, we doesn't care about tomorrow's weather and the day after tomorrow's weather. We usually care about the average of the temperature. In example, is it the temperature in January is lower? The average temperature of January is lower than the February, or how is the rainfall in the rainy season compared to the other season? So it's only care about the general or the average of the climate. So it's only require less amount of observation data, because compared with the NWP, the climate model is the boundary condition problem. It's not the initial condition problem. It can also to predict or the project the climate projection, to simulate and understand the climate change. So it's the definition of the climate model. Yeah, in this picture we can also see that we have include the climate model, also include the biosphere in its calculation. Yeah, and also yeah, it's usually have a coarse grid scale. And then this is the picture about the boundary condition. So if we talk here, if we see here, this is the initial condition, but after that, if we run the model, so with the forcing inside the model itself, it can define where you have to go. Like in the summer, the temperature will go up because the forcing, and the winter, the temperature will go down because the forcing in the model. So the forcing, it should be the forcing is not the product of the model output. It should be input in the model. So that's why in climate, we the important thing is the boundary condition. So it's not the initial condition itself, because we usually predict a long range phenomena. So this is the forcing, the example of forcing inside the climate model. We have the volcanic. So the data from year to year, it should be input in climate model, and also the total solar insolation. Whether in WP, this data is not very important in NWP, because the effect of these forcing data is less if we only predict for 1 or 2 days ahead. The next model is air quality model. It was simulate a physical and chemical process that affect the air pollution in the atmosphere, because it's dispersion processes. She also used the mathematical numerical technique to process and to characterize the primary pollutant that emit in the atmosphere. So there are three in general, the approach method of air quality modeling. First is the dispersion model. It usually in higher resolution, usually in 100 or meter to a few kilometer from the source. And the second approach is the grid-based transport model. Is usually simulating chemically reactive airborne, and it has the wide range of scale. And the last one is the hybrid model, or the blending between those two, the source-based and the grid-based. Okay, I think this is the last example, is the ocean wave modeling. It's usually using the wind data, only wind data from NWP model. So the result of ocean wave modeling is usually depends on the skill of the NWP wind parameter. Yeah. So the advantage of using the numerical wave modeling is first is overcome the difficulty arise in wave prediction due to the random and chaotic nature of the ocean, because it's using the wind data from NWP. So the second one is it's powerful to represent the wave condition in the fine grid of the regional and global area. And also the important thing is the reduced costs when doing mathematical calculation using the complex equation and long data set. So this is only the picture that I'm taking from ACMWF of the global significant wave height and mean direction. And also this is from the PACIOS, the Pacific Center of ocean in the right hand side. Okay, I think that's all for this session. If you have a question or anything you want to say, we still have the asynchronous session should be told by the committee in detail, maybe after this session. And this lecture only cover the general information or the basic information that can deliver you to the next module in this training. So for the detailed explanation about the NWP, about the equation, about the parameter recession used in NWP, I think it will be covered in other model. And okay, once again, thank you for your attention. I hope you enjoy this lecture, and Okay. Thank you very much.